Words in motion. Extracting interpretable control vectors for motion transformers. Transformer-based models are widely used in many applications, but interpreting their hidden states remains challenging. In this work, we explore whether motion transformer hidden states exhibit interpretable structure. Leveraging this structure, we fit control vectors by comparing hidden states with opposing features. At inference, we add these vectors to hidden states and modify and control our outputs. To enhance the interpretability and controllability of these vectors, we refine them using sparse autoencoders. Doing training, top-layer representations of transformer encoders form semantic clusters, which collapse to their class means by the end of training, a phenomenon known as neural collapse. A high degree of neural collapse indicates a well-separated latent space, which allows us to fit precise control vectors between opposing features, such as high versus low speed. Similarly, we fit control vectors between acceleration and deceleration, pedestrian and vehicle, and also left and right turn maneuvers. We obtain the required labels using weak labeling. As expected, the similarity between these control vectors is notably high. This aligns with expectations, as speed and acceleration control vectors, as well as the agent vector, are all associated with faster motion. Here we show the basic architecture of a motion encoder in a motion transformer. It takes motion tokens, which represent past trajectories, as input. These tokens are processed by a stack of modules. Each module updates the hidden states, shown here as H0, H1, etc., which carry the internal representation of the motion sequence. These hidden states are then passed to the motion decoder, which generates the final prediction. We attach a probe to the hidden states to evaluate whether interpretable motion features, like speed, acceleration, or direction, are embedded in the latent space. They allow us to measure the degree of neural collapse. These probes are trained independently. Once we confirm feature separability, we use pairs with opposing features and compute their element-wise differences. Then, we apply principal component analysis and extract a single control direction for each feature. These become our control vectors, shown on the right. At inference, we scale these control vectors by a temperature parameter, tau, and add them to the hidden states. This allows us to modify the model's predictions in a controlled and interpretable way. In this video, we show qualitative results on how scaling the speed control vector allows us to modify future trajectories. More importantly, the changes are not arbitrary. The forecasts remain consistent with the driving environment. Here, we show how applying control vectors to all traffic participants affects their future trajectories as the temperature parameter varies. Now that we have fitted our control vectors, we ask whether we can optimize their linearity. Sparse autoencoders enforce sparsity in the latent space and disentangle features into distinct, interpretable components. We first project the hidden states into a sparse intermediate dimension, compute our control vectors, and then, using the Johnson and Lindenstrass lemma, we decode them back to the original hidden space. In this way, we obtain linear control vectors that can be applied at inference using only a scalar vector multiplication and an addition. We evaluate our approach across different layer types and activation functions, including convolutional layers and MLP mixer blocks. As expected, sparse autoencoding results in a more linear relationship between control vector, scaling, and forecasts. As shown in these figures, where a plus and minus 50% change in output is plotted against control vector temperature, tau. Jump ReLU compensates for feature shrinkage, leading to a narrower range of temperature values. This effect is also reflected in the R-squared linearity metric. In conclusion, we take a step toward mechanistic interpretability of transformer models for time series forecasting. We uncover latent space regularities in motion transformers, where interpretable features are represented along distinct directions. By identifying functionally important directions between opposing features and refining them with sparse autoencoding, we achieve more linear and controllable forecasts. For more details, feel free to check out our paper, An Open Source Implementation. Thanks for listening.